Let's have a look at the second order energy correction. The second order energy correction we get from zeroth order or reference state, the first order Hamiltonian, and then we have to have a first order correction to the wave function. That gives us second order. So now we need our first order coefficient. We expand in all the set of zeroth order wave functions, which here in Møller-Plesset perturbation theory is all Slater determinants, and we have to multiply them with this coefficient here. So what we're going to get is 0 h prime, and then now here we get a sum over j not equals to 0, and then this all the other zeroth order states, which are Slater determinants, multiplied with this coefficient. And then of course I can move or should move the summation in front of it. So I get what one calls a sum over states expression, where I have two matrix elements or transition matrix elements, because I go from my reference state, my zeroth order wave function, zeroth order approximation to the wave function, to another of those unperturbed set J, and back to it. And down there I have the difference between the zeroth order energies of those two states. And yeah, well, I'll remove that later. Now, we discussed that those zeroth order energies, those are the sum orbital energies. Those are the sum of the orbital energies. So that's the sum of the orbital energies of all the orbitals included in this reference state, our STF, Hartree-Fock orbitals. So those are all the sum of all the orbital energies of the occupied Hartree-Fock orbitals. That is some other Slater determinant, and this is the sum of the orbital energies of all the orbitals included in that Slater determinant. And these are just normal matrix elements over this fluctuation potential here of different Slater determinants. So it's all up to Slater-Condon rules now to figure out A, what this becomes, and B, or maybe A first, which kind of Slater determinants actually can contribute here. For that we have to go back to our operator H prime and discuss it in a bit different way. We have to discuss it now with the eyes of, we have to use the Slater-Condon rules in order to figure out which of them are contributing. So what kind of operators do we have in our H prime, our fluctuation potential? Well, this is quite obvious. Ri, Rj, that's a 2-electron operator. So we have a 2-electron operator in here. But what is this? What is this Hartree-Fock potential? Is it a 1, a 2, a 3, 4-electron operator? That's a 1-electron operator. Yes, this is a real 1-electron operator. And unfortunately, I removed it now. I had expressions standing there for those Coulomb exchange operators. They have the second electron in there, but they have an integral over the second electron. So there is an integration of the second electron already included there. So it is actually just an operator for one electron. So we have a 2-electron operator and a 1-electron operator. Now, this is our STF, and let's just write it to make it clear. That's our STF, Hartree-Fock determinant. And all the other determinants are then going to be single excited, double excited, triple excited, and so forth. So what kind of J can we have here? What can that J be if we have a 1 and 2 electron operator? So we have the highest is a 2 electron operator, and from STF with a 2 electron operator, to which other determinants can we get? That's the same question we discussed when we discussed the CI Hamiltonian matrix. Nikolai?
So that's the Slater-Condon rule, so we can go to 2 up or 2 down.
Right. You can, if you have a 2 electron operator, the difference can be 2 between them. Now, since that is the STF, we can go up to double excited. So that can be either single excited or double excited determinants. Or let's write it in the other notation which we used before. Then we use the one which we actually sort of wrote up. This is a single excitation, and IJ2 occupied 3 placed by 2 virtuals A, B is a double excitation, double excited determinant, or double replaced determinant, but they are called double excited. So no triple excitations, because a triple excitation, then we have a difference in 3 orbitals, but we only have a 2 electron operator to connect them, and then there will be 1 orbital which is going to be different, and therefore it's going to be 0. So that's Slater-Condon. Condon rules. So only single and double excited.